we need a narrative. And as we discussed last time, even though we construct an historiography, and even though sometimes those historiographies are flawed, we'll look at an example of that this morning if we have time, some flawed Egyptology, and namely, of course, anachronistic retrojection of our current knowledge, state of knowledge, into the past, and then judging the past through an anachronistic lens of the present. And that's called, of course, presentism or Whiggism, or simply stated anachronism. And that is an alluring temptation for the historian, and it's very easy to do. And one notable example of this, and we won't get a chance to really discuss it in depth in this course unless one of you would like to take it on as a project, but some of you may have run across the book Inventing the Flat Earth. And this book concerns the historiographical error that has been promulgated since the 19th century, that everyone up until Galileo believed in a flat Earth. That is simply not true. As a matter of fact, really no serious astronomer after Pythagoras ever held to anything approaching a flat Earth. All of those folks spoke of Earth as a sphere. And that was the only place where they got it wrong. I mean, for example, Aristarchus, in calculating the circumference of the Earth, we'll talk about him when we come to the Greeks here in 2 or 3 weeks' time. Aristarchus, of course, was calculating the circumference of a sphere. And of course, the Earth itself is a spheroid, which is why he was off in his calculation. And it was simply because of when he parameterized the problem, he parameterized the geometry of the Earth as a sphere. We'll speak about geometry, but this particular book, I believe the author of Inventing the Flat Earth is Thomas Friedman, if I'm not very much mistaken, and I stand to be corrected. Thomas Friedman states that this is a 19th century invention by historians, and as a result of it, they are attempting to, there are always several ways that one can build the highest building in town, and one of which is simply to tear down all the buildings, and you will have the highest building in town, but at the expense of tearing down all the other. Well, in many ways, this was a 19th century post-Enlightenment way of saying, look, we have the tallest building in town, and look at the poor benighted ignorance of those who have gone before. So it's easy to retroject these types of things into the past. So as a result, we have to choose a starting point. We do construct narratives. These narratives are built on shaky foundations, to be sure, but nevertheless, we have them in terms of conceptual access, and we can always go back and critique them later. So let's start with taking a look at the Egyptians, and to make sure that I have got this other screen at the ready here. You should see before you, I don't know what is going on there. The Andromeda Galaxy. And I hope that's what everyone can see. Indicate by, let me see here. I'll just do here. I'll open the chat over here, and okay. All righty then, let me start our Egyptian saga here. Okay, very good. Our Egyptian mathematics, and I'm hoping to get down into the geometry and the algebra today, we may only get as far as the arithmetic. So you can see that. To put things in perspective of known human history, and I am not an anthropologist by training, so I'm reliant on others, but you will notice several salient facts of this. But really, we're dealing with something much more recent than 35,000 years ago. And then, of course, you can see, so we're dealing really with the late Paleolithic age on. Now, if you're interested in the lower Paleolithic and the middle Paleolithic, there is and especially if you're interested in that period of time in Europe, there is an archaeologist. I think she is still active in her scholarship. I'm not certain, but by the name of Gimbutas, Marianne Gimbutas, if I remember correctly, who has done a lot of work in this middle Paleolithic age. And of course, she does connect and contextualize, but her main emphasis is on these ancient cultures, especially cultures in Europe of the Great Goddess and all this type of thing. Very, very interesting and very extensive archaeological and work that she has done. But more specifically, let's come to the Neolithic age, and we'll take a look at Egyptian civilization. And of course, the pyramids date back to 2600 BC. Immediately, we think of the pyramids in Mesoamerica. And they're also, by the way, just as an aside, I don't know if any of you hail from either from Southern Illinois or from Louisiana, but there are remains of mounds and pyramids there. I think of the Great Serpent in the Ohio River Valley, not far from Cincinnati. I think of and then there were pyramids on Montauk. So for those of you who are from or who have visited Long Island, out on the farthest reaches of Long Island, out on the far eastern point in the Atlantic, Montauk with the pyramids. So we find the pyramidal culture pervasive throughout the world of this time period. Now, I will say too that Kotz does a good job of contextualizing, but he doesn't have the room to provide all of the dates and the detail that we're able to achieve here. But then you will find that we have then Egypt of the pre-dynastic period, and this would be around the time of the rise of the Hyksos kings. You have this divided, Upper Egypt divided into three parts, the Badarian, the Amaratian, the Gerasian cultures, and then Lower Egypt divided into two principal cultures, the Fayum and the Merimna. And you will notice there that there is some overlap in the dates, although there was an interplay that Upper Egypt would rise and Lower Egypt would rise. And then you have the Hyksos who come through, which were essentially Bedouin rulers who come, and then we find a unification of Egypt. Interestingly, for our purposes here in the history of mathematics, we find that there's a 365-day calendar by 4200 BC. So that would correspond to the Badarian culture in Upper Egypt and the Fayum culture in Lower Egypt. And then we also have numbers, evidence of numbers calculated in millions from around the time of 3100 BC. And I mentioned last time the psychology of numbers and the psychology of numeracy. And you'll see that in the case of, for example, the work that has been done with the consciousness and cognitive abilities of babies, infants, and their study, the emergence of numeracy. And then you see a similar, I guess you might say, history of psychology approach to these two ancient cultures. Then we spoke last time of a calendar of base 12. Let me just mention very quickly. Our bridge, of course, is 365 days, the 365-day year. Okay, so as early as this time period in 4200 BC, the Egyptians had a base 12 calendrical system, and each of those was on a base 30 system, and in the 5 extra days. And that's been dealt with in a variety of ways in cultures throughout the history of the world. By the way, in the history of science, and by default in the history of mathematics, the calendrical reform and the history of calendars is very much a complete field of inquiry. So if any of you would be interested in calendars for a semester project, I definitely encourage that. And I have had students in the past who have worked on Mayan calendars, and who have worked on other Aboriginal calendars. And I've had students who worked on the Julian versus the Gregorian in the European system, how that was reformed, because there are so many details there. But the idea here is that the Egyptian calendar is one of the first to be based on the solar year and the diurnal rotation of the Earth around the sun. And so as a result of this implies then the knowledge of astronomy and mathematics. When we come to the early modern period, the great mathematician Johannes Kepler, when he was working on attempting to reconcile, well, let me rephrase that. His philosophy of the Earth and the planets in their orbits in ellipses was born out of his reform of the tables, astronomical tables. So that was a byproduct. He had accumulated these data. Tycho Brahe had accumulated observational data for 20 years before him. Then Kepler had his own observations. And finally, he puts those together, 1609 and so on, and says that, look, on Mars is only 3 minutes of arc off of a perfect circle. Therefore, the Earth must orbit in all of the planets must orbit in ellipses. And this was born simply out of the knowledge of accumulating these data in an attempt to reform and have more accurate astronomical tables. And the same way would apply to ancient Egypt. Then we have the dynasties here. And so again, Great Pyramid, we're speaking about pyramids in Aboriginal cultures, 2600 BC. So that would be roughly in the early dynastic period. Then, interestingly, I read on Tuesday from the Moscow papyrus, the MMP, that contains the 25 mathematical problems we discussed. And that's from 1850 BC, which would be in the Middle Kingdom period, dynasties 12 and 13. For those who are specialists in the field, the pyramids themselves are an entire graduate course. Dissertations can be written. Indeed, whole careers have been structured around pyramids. So I'm going to leave that for the moment. And the study of the geometry of the pyramids and so on, I'll leave that for the moment. But anyway, you can consider that. And if you're interested in taking on that particular field of inquiry, then you're certainly welcome to do so. Then another papyrus we will examine today is the Amos papyrus with 85 mathematical problems. And that comes from the period approximately 1650 BC. And that would be in dynasties 14 to 17, which is the second intermediate period. And one can see so many of these. Incidentally, for the purposes, for those who are interested in biblical studies, you will note the Kushite domination in the 7th century BC. And then you'll notice here also the Persian period. And then this paves the way that later then Egypt becomes a Greek colony, or large portions of what was once Egypt of Upper Africa there becomes part of that. And then we see the rise of Alexandria and so on. But that's another topic for another day. All right, so now we come to the Amos papyrus, or it's also known as the Rhind papyrus, named after Henry Rhind, its discoverer. It states that it is a thorough study of all things. It has insight into all that exists, and it has knowledge of all obscure secrets. But along the way in here, we have methods for multiplication and division, as well as geometry, and I'll come back to that later, together with 85 problems along with their solutions. So this is how we know Egyptian mathematics so well. Well, let's take a look then at the Egyptian number system. Now, another way we were able to one way we were able to have such a great interpretive insight into these matters is that with the discovery of the Rosetta Stone. And the Rosetta Stone is itself of 114 by 28 centimeters. I should have brought also a photograph of the way it looks sitting in the British Museum, but if you're interested, you can take a look. It has 3 inscriptions that have 3 different, that has a single text, but it's in 3 different variants. So you can see this is the first variant, second variant, and third variant. So one sees, of course, more of a hieroglyphic type writing. One sees then more of a cursive hieroglyphic writing, and that is the term that Egyptologists use for it. And then one sees then the translation of that. And let me see if I can move this over here. And then we have the Greek. Well, the beauty of that is because we have the Greek, think about this, going back to 1822, and we have the French Egyptologist Jean-Francois Champollion, and he finds and begins examining this Rosetta Stone, realizes this is the same text in 3 different forms. This is the interpretive key. And because scholars at that time, of course, obviously knew ancient Greek script, I mean, and especially with the Attic Greek script that's used here, if you can see that down here very clearly, and they have an interpretation, then he was able then to develop a key to interpreting hieroglyphs. And then he was then able to take this and create a glossary, and then be able to go back and uncover and decipher everything else. And so it is the Rosetta Stone to which Egyptologists really owe their allegiance, and the way we have knowledge of the ancient world as much as we do. Well, you'll notice that here's a close-up view of some of the hieroglyphs. And then, of course, later, we see that Egypt Egyptian language evolved in 3 stages. By the way, the hieratic means that which was written by the priest, and that's more of a cursive hieroglyph that I referred to earlier. It's a further development of a cursive hieroglyph. And then, of course, the Coptic language emerges, and you still have that today in Egypt, of course, with the strong admixture of Arabic. Now, of course, you also have the Coptic Orthodox Church. That's an entirely other matter. There are some really wonderful Egyptological treasures that have been preserved by the Coptic Church itself because of the antiquity there in the ancient Coptic texts and so on. But that's a little bit more this side of the hieroglyphic period. Now, if you look at this, this is an account book here, and you will see here that that you've got some of the numerals down here, representation of those. And so you notice that you've got 4 tadpoles below the oxen here. And when one has a tadpole, the developing frog, as it were, then each of those is in a unit of 100,000. So that would indicate 400,000 oxen. And then over here, we have the sky lifting god behind the goat. That's a hieroglyph for 1 million. And I've got the text down here below in case you want to refer to it. And then you've got 4 tadpoles there and 2 fingers. Each finger is 10,000. And then you've got the lotus stalk here, which is each stalk would be 1,000. So you've got 2 of those. So you've got then 2,000. So according to this accounting here, then the king would have had, the Pharaoh would have had 3000 BC, would have had 1,422,000 goats. And that would be the accounting of it. And then, of course, over here, if you want to look at here that you have the animal you have the prisoners there. And so we find that he has 120,000 pyramids. And according to Egyptologists, this represents some of the earliest surviving document of large numbers from anywhere on Earth. Now, of course, with the Needham hypothesis, that may be contested. And of course, now we still have pictographic languages that live in our world today. Think, for example, one really strong example is Chinese, since I've referred to Joseph Needham the other day and the Needham hypothesis in science and civilization in China. And so pictographic languages are not dead. They're certainly very much in use. And when we think of European languages and when we think of English and the letters we use today, this very day in the 21st century, some of the letters we use are based on pictographs, that they're shapes representing certain objects and so on. And we use pictographic language in teaching children the alphabet and to read. So pictographic language is not that far from us. We just don't realize how dependent we really are on it. And in many ways, the written language we have, all of this text we have here in English here is, we read it, and these are shapes in many ways that represent sound. So even though they're shaped into letters that our mind psychologically interprets as a whole word, or if we're speaking aloud, if I were reading this to you, then I would interpret that as representing the sounds that I'm making with my mouth. But the sounds I'm making with my mouth and the language here on the page are not one and the same. Philosophers of language have established that. In many ways, it is still a pictograph, regardless of the language that we speak. But anyway, enough about philosophy of language. I find linguistics fascinating, and no historian can ever be very far away from linguistics. Now, as we've established, this Egyptian number system is additive. Now we have our systems of ones. By the way, if it will help you to work through this system, and there are a few exercises just for fun, I wanted to give you experience in working with the system. In our first homework, we're going to be working mainly with Egyptian numerals. And I don't know if any of you who are pre-service educators, and I need to bring up I wish there were a way to bring up my participant list again. Let me see if I can get you up here. Yes, I've got you back. Indicate if any of you has taken the course, you can just do a thumbs up or a raise of hand. If any of you has taken a course in mathematics teaching, especially mathematics for secondary or elementary. Has any of you taken a course like that? Oh, great, fantastic. Okay. All right. In those courses, generally we will cover Egyptian numerals. And I will tell you also, we did have a few years ago in Perspectives, a student chose to, or a group decided to provide a lesson on Egyptian numbers. And this is really good for working with young children in acquiring math skills, and especially children who are still working on language development, because there's so much overlap in those early years. Even right up through elementary, there's so much overlap. And as I tell my math students, even today, even in university math courses, math is 99% communication after all. It's numerical, it's symbological communication, but what form of language isn't? But anyway, in that, as you took that course, you probably had a section on Egyptian numerals. And it's good for us to have this as an alternative method of teaching numeracy in our educators' armamentarium. But it's also good to have it because it makes us stop and reflect on our own practice of numeracy. So we have so if you wanted to set this up and have a chart of maybe hexadecimal and binary in juxtaposition to this, be my guest. It's a fun system. So we have here, we have our system of ones, just simply represented by these. So often scorekeepers will use this, so that's a very Egyptian system. When we get up to 10, we have the curve here, the horseshoe or the upside down U, whatever you want to call it. When we get to 100, we have the curl here, which looks to me like a path of a particle in a cloud chamber. It's describing that spiral path. And then, of course, we have the sky god, the 1 million, the frog or the tadpole, 100,000, the finger representing 10,000, and the lotus stem, which is what that is. This is just the flower, and these are supposed to be the leaves, 1,000. But you can put several stalks on one plant. So if you want to do 3,000, you could just put some more blossoms out here. And so then it's easy to interpret this. We've got here the 3,000, and then we've got the 200, 40, and 4. Okay, easy enough to read. So then we've got 1, 2, 20,000, 1,000, so 21,000, 1, 2, 200, 1, 2, 3, 37. So there you go. Egyptian system is additive. All righty then. Let's move ahead to some more. Let's perform an addition operation here. Now, in this case, it's simply a pooling of symbols. And I think, and I'll just let you look at that on the screen. I think looking at that, whether you're even if you're an auditory learner, I think this is something that's easily taught visual, which is why it works so well with younger students. With me, I have to manipulate them, but even this particular representation, I can comprehend it fairly easily. Okay, so we have up there, it's I think now self-evident, we have 365 up at the top. So we would have we would have those, what I call the particle spirals there. And then we have 1, 2, 3, 4, 5, 6 of these horseshoes. Then we have 5 tallies. So all we have to do is pull these together. If you want to set these up, and in the homework, you could just set these up, draw a line as we do in standard addition problems, and then just pool them down here. Now, once you do that, though, when you pull all these together, you'll have 6, let's see here, 6, 7, 8, 9, 10. So that gives me 10 of these. So now I have 100. So I can eliminate some of these over here. Once I have my 9 here, and then I can just pull it over and I can add another spiral over here. So we'll have 1, 2, 3, 4, 5. And then so we have 5 spirals. That will give us 6 spirals. And then that will obviate all of this over here and bring it down to 1. And so you can see how that goes. So the total number here at the end that you wind up with will be 622. Now, you might ask me, and you've already seen this already, spotted this already, why, when I pool these, do I not just have one of these horseshoes? Well, I do. Well, might you ask, but when I pool these together, I have more than 10. So then I take the 10 and that brings back another horseshoe. And then that gives me 2 remaining here. If you want to work this way and start with just the tallies here and work your way up in a system of 1s, 10s, 100s, you could do that, and so on. Any questions or comments about that? It's fun, and you'll get a chance to do some of those in COTS. I have COTS right here, we've got. He also has. Well, we'll talk about that later, but he also mentions the geometry, and he doesn't go into really as great a depth. Now on he does cover this on page 4, the addition, and he also discusses the multiplication, which I'm going to come to in just a moment, and then also the geometry, which I don't know if we will have time to get into today. But let's take a look at multiplication here. Okay, so we have multiplication. Let's take a look at this. We have, we're going to multiply 23 times 13 here. All right, so the Egyptian way of doing things, of course, would be to factor down the 13, but not in a sense of mathematical factoring as we know it today, but to break that down into a system of 2s, multiplicands of 2s. So, and then add those together. So what I'm going to have here, I can, first of all, let's break down the 13 into multiples of 2. So I start with 1. Now we know, of course, that's prime, but all right, that's another issue for another day. But so I subtract 1 from 13, and that leaves me with 12. And I can break 12 down into multiplicands of 2. I can break that down into 4 and 8. Okay, and COTS goes into covers this on page 4 if you want a slightly different approach. And then so we put our 23 up here. So we have the 2 horseshoes and the 3. So we have 23 up here. So we have 23. We have 23 times 1. That gives me 23. Okay, sounds good to me. And then I set up my 2 out here. So I have 23 times 2. So all I have to do to have 23 times 2, which of course we know is 46, but all I have to do in the Egyptian tallying system is just repeat that. So I have 23 and I have 23 times 2. So I have 23, 23, and 23. Okay? So I've got that. So that's out of the way. Now I come next in line to the 4. I could do the same thing down here if I wanted to. There would be nothing to prevent me from going 23, 23, 23, and 23. There would be nothing to prevent that. This is just collated to make it a little bit less awkward. But if you wanted to repeat that same thing down here 4 times, 23, 23, if you wanted to repeat this thing here 4 times, there would be nothing wrong with that whatsoever. Okay, so, and then we get to 184, which is 23 repeated 8 times. And then we pull that all together. And then at the end, we just add all those together. And then once we add those together and pool that, then we find our result of 299. So I will leave that up to you, however you want to set that up. If you're teaching this to a younger student, especially maybe if you want to use this as an enrichment exercise for students who may be learning elementary multiplication, you might want to keep that and just repeat those 23s over and over again, and then let the students pool it down here at the very end, and then say, okay, now let's go back and convert it and reduce it down to the spiral path and the horseshoes and the strophes and so on. Okay, so anyway, you know, we can double these numbers clear on out. I mean, you can see that. And so here again are some more examples of ways we would break things down. 11 would be broken down into 1 and then 2 plus 8. We would break down, of course, we've already done the 23. Then you could break down 44. Will break down into 4 plus 8 plus 32 in that case, and we won't have a 1 there. Because now we know today, of course, 44 is non-prime. So, you know, that's one thing that we can do. I want to come back to, well, let's see here. I'm going to go ahead and talk about binary expansion just a little bit. We'll come back to that in a minute because I want to go back to some archaeological materials. And I apologize for putting the cart before the conceptual horse here. But at any rate, you know, any integer n can be written as a sum of powers of 2. Yeah, well, okay, that's math, a mathematical principle we use all the time. And we can start with it. You can see it represented here, that where we have 2 to a certain power of k is no larger than n, and you can subtract it and repeat the process. So, you know, this is the same type of principle here. So that's essentially what we're doing here is a binary expansion. Oh, and also this is a little bit out of order, but okay. We'll just review that this is an application of the distribution law. And I'll just let that lie for now. We'll have plenty of time to come back and discuss that. But you can see here that this in retrospect is what we did a while ago. Okay, so now let's talk about division. In this case, you can see we have a division, and of course, in the Egyptian mind, you can set up division as just a fill in the blanks multiplication problem. So because we know what the product is, and we know what our first number is, we just don't know what the multiplicand is. And so we're trying to find that multiplicand. So in this case, what is our, multiplicand and so on that we would have here, which of course in the case of a division problem would become our dividend. But either way, I think just leaving it this way, and if you're teaching it again to the younger student, I think it's best and less conceptually treacherous if we just leave it in that way. So we've got our we know that we have our, we know what our initial, we began with 23 and we have a product of 299. And so in this case, then it is simply a question then of filling in the blanks. And so once we do that, then we can find out, then we can factor down the 299. And so as a result of that, then we find out that, okay, we already have our 23, so we subtract 23 from 299. And then that's going to give us then our, that's going to give us our remainder of 276, if I'm not very much 276, if I'm not very much mistaken. And so as a result of that, then because we have that, then that can be, and we know that that's remaining. But here's the thing about that. We've got 299 and we all already know that we can pull 23 off of that. So we pull the 23 out of this pool down here and what's left over from that. Okay, so from that, then all we have to do is find out, divide that down further. And once we do that, we just simply find out, all we need to be able to do is reproduce this pathway of the 1, the 4, and the 8. And when we add those together, then we come back to our initial 13. And there is an example of that, if I'm not very much mistaken, on page 5. Let me take a look here. 5 and 6 in COTS of breaking that down into that dividend. So in other words, we know that in order to get to 299, we're going to have our 1, which is, we already know that going in because we have 23 there. And then we multiply 23 times 2. That will give us our 46 and so on. So we're just rebuilding this same equation. So to the Egyptian mind, a division operation is simply a case of starting here and rebuilding this middle part here, these middle tallies. That's all it is. And then once we wind up with these out here, we realize, oh, okay, I'm going to have to go up to a multiplicand of 8 in order to come back full circle to 299 where I began. Because I pulled the 23 off, then I have the 92 here, and I have, of course, the 184 here as well. And then to get back where I started, then of course I just simply have to add these together, and that's going to give me my 13, which is my dividend, or my multiplicand more correctly. All right, so there are numbers that cannot divide evenly. And of course, that's a mathematical maxim, but nevertheless, let's take a look here that we have 35 cannot be divided evenly. Okay, well, we can divide 32 by 8. So 8 times 4 is 32. Okay, that's recognized. But then what are we going to do with the remaining bit there? So, okay, so we've got 32, which is, we've got 35, which is 32 plus 3. So we have 3 remaining. So thinking in terms of remainder. So we have 3 remaining. And then you will notice here that in terms of that, you've got the case of what we call, we do doublings and then we take halves. So we have here a 2 remaining. So we have a chart of halves. We'll go into that in just a minute. I'm going to show you the symbols for this in just a moment. But so if we have 4, that would be a full half. We don't have a 4 involved, but we do have a 2 involved. So that is 1/2 of 1/2, which will give us 1/4. And then of course we have 1, which is then a 1/2 of a 1/2 of 1/2. So that's 1/8. So at the end, we wind up then with these factors becoming 4 plus 1/4 plus 1/8 in the Egyptian system. Now, when you see this shape here, this would function as a denominator of 1 right here. So when you see this, and this would, you can read this as a quotient. So you would read this as 1/10. And then, of course, down here, you would read this as 1/123. So this is always the denominator up here. And then this, of course, is the numerator. Let's take a look at this. So we add these fractions together. So we have 1/2 plus 1/4. And of course, that will give us 3/4. Of course, we know that from a simple addition of fractions. This may be another tool that you can use when teaching the younger student the addition of quotients. In terms of greatest common factors or least common factors, all that type of thing, when you look at that, you can use the tally system, because remember, I've got this numerator up here, and then you can treat this exactly the same way that you would treat, that you would deal with least common factors in 21st century mathematics. And you would have to show them that this is worth 2 of these, because 1/2 would equal 1/4 plus 1/4. So another way you could teach this is just simply then convert that then, and maybe draw a couple of lines down in here and convert this into this shape over the 4 bars, and then again this shape over 4 bars. You could do something along those lines. Then you can get into more complex situations, such as 1/2 plus 1/8. Well, it's going to take then 4 of these then to equal 1 of these in value, and so on. And you notice here that the Egyptians go ahead and decompose it as a sum of those two. Anyway, that's another topic that we'll come back to momentarily. And then you can see here the same thing with using 18ths. And it doesn't matter, it's still a quotient. You've got this up here indicating 1, and then you have, of course, this indicating 10. So 10 plus 8 is 18. So you have 1/18 plus 1/3. And then, of course, again, you deal with those again as you did. So it would take, again, 6 of these to equal in value 1 of these. 6 of these to equal in value 1 of these. All right. And again, this may be overblowing my case. Again, you can see this using the visual of dividing the pies. So divide 5 pies equally to 8 workers. Each gets a half slice plus a 1/8 slice and all this type of thing. So you can decompose this down into its constitutive elements, and you can see that with these fragments. So you would get each of the 5 workers would get a half slice and then a 1/8 slice. Each of the 8 workers, I'm sorry. And so let's take a look here at these. We have cases of these fractions, and we'll see how far we get in this. And let me see here. let me check something here. All right, good. I'll go on into the fractions a little bit farther. I'm not sure we can get a chance to talk about the geometry as much today and so on, but we'll take another look. Okay, so here we have repeated use of fractions. And you can see examples of this. I mean, arithmetically, we encounter these every day in mathematics, similar to this, you know, and we can break these down into the constitutive elements and so on. I won't go into all this, but of course we can break 3/5 down into adding, you know, together, you know, 3 of the 1/5 as is done here, and then you have, then we can break down the 1/5 themselves into constitutive elements of 1/6 and 1/30. And then you can do this as a combination. You can throw a 1/15 in there. Anyway, that we will develop this a little bit more later, because later we'll use this in our geometric series and all of that later in the course. And then you can break this down even further and look at this vast assemblage of values that we have here in the denominator. Well, there are some principles at work here. And can we do this in the Egyptian context? Yes, yes, we can. So let's take a look at this here. Let me see here. Okay, so there are you notice that we decomposed this previous down into, you know, finally 1/5 was decomposed down into 1/5 plus 1/6, all this and going on and on. Now we wouldn't need to do that for 3/5. You know, in Egyptian mathematics. I mean, we would just draw that symbol, the symbol of the eye, and then have 5 bars, and then just add those together, and you'd have 3/5. But in complex situations, we do need to break it down. So are there ways we can break these down? Yes, there are fraction decomposition tables in Egyptian. Primarily the 2/n and the n/10, because remember, you've got that fraction, you just have that single I. How do we represent larger numbers in the numerator? Well, we're going to need a way to represent that. And moreover, then when you're talking about tenths, so many tenths of something, you need to be able to break that down. And of course, this is done in the context of the aha, which would be these heap problems. You can see that, and then dividing loaves, you see that sometimes in the pictographic language, and the hecats of grain and beer and so on, that you can see these there. And also you can see this applied to geometric problems as well, which we'll come to in time. So here are some of those tables, these decomposition. And I apologize for the blurriness of this. I pulled this in here. I think this is from the British Museum, and it looked, when I put it in, it looked much more usable than that. The resolution is very high. I don't know why it blurred on us. On my apologies, folks. But this is an example of one of the decomposition tables. So let's take a look at the n/10 table. Here we have, of course, 1 divided by 10 yields 1/10. And so, okay, that sounds good to me. 2 divided by 10 yields 1/5. 3 divided by 10 yields 1/5 plus 1/10. 4 divided by 10 yields 1/3 plus 1/15. And 5 divided by 10 yields 1/2. It is a way of keeping 1 as the numerator. And then you will notice that we get clear down here to, we notice we have 2/3 in here. We'll come back to that in a minute, because we have a 2/n table that we can go to, and we'll be able to fix things there. Just thinking today, I wanted to go into the Egyptian algebra and the Mesopotamia. I'm just thinking here, since we're at 10:35, I wanted to let me just quickly, we'll take a look at those tables. Let me just take a quick look here, folks, and you'll look at the Andromeda galaxy for a while I take a quick look, because I don't have time to go into, because I want to start dealing with the multiplication. Pulling these quantities together. I don't know what happened to my 2 over n table. I don't want to take up your time trying to find it. Well, just a moment, folks. I'm going to take a quick look here, because I do have it in my files here. And we can take a quick look here and see. That was my apologies for this. I didn't. I'm going to stop that screen share for just a moment while I do this. Okay, let's see here. We'll take a look at this here. And dividing with fractions and that type of thing, which we need to be able to do, the n over 10. Thought I had the 2 over n table right here at the ready. Oh, yes. Here it is. Okay. Let's take a look at this. I've got this table over here. Yeah. Yes, I do. I'm going to put this up on the screen, and we'll end with a discussion of this. Okay. And I don't know why this is not going into. Okay, here we go. All right. So remember we did the we used the previous table to decompose everything down in terms of something over we did the value of the breaking it down. If we have the n over 10 table. Okay, so now we've got and remember we had a result of 2/3. Okay, this is the table that one uses to break over the 2 over something, because inevitably when we decompose in that fashion, we're going to wind up with a numerator of 2, and we've got to deal with that some way. So we decompose it into these forms. So let's decompose, like, for example, we've got here 2/3, which would be equivalent to 1/2 plus 1/6, 2/9, 1/6 plus 1/8, 18th, 2/5, which will enable us to decompose into 1/10 plus 1/30th, 2/21, which we can decompose into 1 over 14 and 1 over 42. You get the general idea. And with our knowledge of factoring and prime numbers and all of this type of thing, and with our being able to find greatest common factors and least common factors and all this type of thing, this is a variation, but a very special variation on that theme. Our parameters are that we can't have a numerator larger than 1 when we're attempting to add fractions together. And so we've got to find a way to convert it in these forms, represent it then pictographically, perform the addition operation, and then we can, at the end of all that, then we can pull it together and simplify it again. But simplification is not as important in this case, because we'll have a pool, we'll have our quantity there. And it doesn't matter, the simplification we're going to do will be pictographic simplification. So if we have more than 10 of the single bars, then we make a quantity of 10, which would be the horseshoe, and so on. so we can build it back out where whence we first began and that type of thing. So that is the table. I ought to try to, I tell you what I'll do, I'll provide that for you as reference so you can have this because if I'm not mistaken, COTS does not provide this table. And you need to have access to it in order to work on this section. So I'll make sure you get this here. And my apologies for not having it earlier. Well, our time is fleeting and I must end there for the day because I don't want to go ahead and deal with the algebra and geometry. So we'll deal with that next week. But are there any questions or comments before we leave for the day? Oh, here we have chat. Oh, okay. Someone was asking for the homework, do we write the final answers in Egyptian numerals? Yes. Yes, that's to give you practice in doing that. That can be fun. And you can also write your answer also in Roman numerals next to it, or really Arabic numerals, I should say, not Roman numerals. We'll get a chance to do Roman numerals later. Your call, but preferably Arabic numerals and the Egyptian numerals in the homework. And I will be happy to post the slides and we'll have that there. Really looking forward to next time. So anyway, thanks to everybody. And I will be around virtual office hours starting at 12:15-ish today. So if you need me, you know where I am. I'm also in Jester if you want to brave the cold and come over here. But at any rate, I'll be glad to hear from you. And thanks to all those of you who have already contacted me. It was great to hear from you, and I look forward to working with you. Well, with that in mind, then I guess we will end right there. I need to get the Andromeda strain down off of the Andromeda strain, the Andromeda galaxy. We'll talk about the Andromeda strain a little bit later in the course. So, all right. Well, if there is nothing else, we'll end there and have a wonderful day in mathematics. And we will see you then on Tuesday.